The last concept in this chapter that deals with perfect constructive and destructive interference is called thin film interference. It's also labeled as optical coatings on the test notes. Because optical coatings, for example, if you have a really nice camera, your lenses are likely coated with a thin film to help minimize glare reflections off of surfaces. Another example, my glasses have a blue light coating on them to help minimize the blue light from the screens that can be hurtful to our eyes, essentially. So thin film, we're talking a really, really thin layer of something. A non-practical example, if you've ever been in a parking lot after it has rained, but it is sunny, there you can often see in puddles, if you look at a puddle of water, you can often see a rainbow. And that's because there is a very thin layer of oil or gas, I don't know technically what it is, but there's a thin film of something on top of the water, that puddle. And that film, we're talking micrometers or even smaller, very, very thin layer. And so this thin film, we of course have air above it. Let's say that this thin film is oil. I don't actually know the index of refraction. I'm going to make one up. So let's say this oil layer has an index of refraction of 1.25. Water, we know, has an index of refraction of 1.33. Air is essentially 1. And so what's happening is light rays are coming in. As they come in, I'm just going to draw a line representing the direction these light rays are coming from. When it reaches this boundary of air and oil, some of the light continues through. It's transmitted into the thin film, but some of it is reflected. This reflected light is bouncing off of what we consider a rigid surface. If the N that the light is in is less than the N of the surface it's reflected off of, this is considered a rigid boundary. If you remember with a string, that rigid boundary causes an inversion. So this is inverted by pi halves radians, or half a wavelength. The light that was transmitted and continued in the oil, when it reaches the water level, this is another surface. Some of it will be transmitted, will continue into the water, but some of this will be reflected. Since N of the oil is less than N of the water, this is considered a rigid surface. And so this light ray is inverted as well. Now, as it comes back, it does reach this boundary of oil and air. There will be some reflection and some continuing light. So we have two reflected light rays. The first one was off the air-oil boundary. This second reflected light ray is the one that reflected off the oil-water boundary and is now coming back out into air. This one is also inverted because we have this rigid boundary. So these light rays, these reflected light rays, because both of them were inverted because of the rigid boundaries, both light rays inverted on reflection. Now, coming in they're in phase because they both invert on reflection. They are both in phase right now, meaning we consider their initial conditions as they are coming towards us as being in phase, so a delta phi naught of 0. When we were talking about, the sound waves interfering, like with two speakers, if delta phi naught was 0, we found that delta x, as long as it is equal to some multiple of a wavelength, then we would still have constructive interference, because those waves are in phase. As long as any extra distance traveled keeps them in phase, which means a shift of a whole wavelength, then they will still be constructively interfering. Okay. For simplicity's sake, we are going to assume normal incidence. That's not how I drew it in this original picture, and that's because the picture's kind of hard to imagine. So here's our thin film. If you remember, normal means perpendicular to the surface. So we're going to assume the light coming in is hitting this surface at a right angle, which means the light that is transmitted through hits the next surface at a right angle, and the light that transmits through keeps going. On this picture, the reflected light ray is hard to notice because it's going to reflect back along the same line and then reflect back along the same line. So the reason I drew it at an angle up here is just to better visualize what was happening. But as we assume normal incidence, the reflected light ray, the extra distance is traveled by the one that goes through the thin film. But assuming normal incidence, the light ray comes down, so it travels a distance of d, where d is the thickness of the film. And then when it reflects, it goes back up another distance of d. So the total extra distance this light travels is 2d. And that is specific to this normal incidence. If it's not at normal incidence, we would have to know what angle it hits at so that we could figure out how far that hypotenuse was. So we are assuming normal incidence. So looking straight down at the puddle, for example. So 2d is delta x. That's how much farther the second reflected light ray travels compared to the first. Now lambda, if you remember, when light enters a new medium, its speed changes based off of the index of refraction of the medium. So the speed in a new medium is the speed of light, c, over n. So c is the speed of light in a vacuum or air, since n is essentially 1 for air. The frequency stays the same. So if the speed changes but the frequency does not, the wavelength in this new different medium also changes. In our equation, this wavelength needs to be the wavelength the light has in the thin film. The wavelength it has while it is traveling this extra distance. And so I'm going to go ahead and put lambda over n here, where n is for the film specifically. So in this example I mentioned, that would be n of the oils. in your test notes, you're going to see a lambda sub c is equal to 2nd over m. But m cannot be 0. If you remember before, m equals 0 meant the waves travels the same distance. But that doesn't make sense in the case of a thin film, because if the waves traveled the same distance, then there was no thin film to travel through. So m in this case needs to start at 1, and there are multiple values for which we will get this constructive interference. So this equation, when you look at the test notes, you're going to see this equation under n of the surface being greater than n of the film, which is what we have, right? Our surface is the water. That's what the film is on. So 1.33 for the water was greater than the 1.25 for the film. In that situation, to get constructive interference, we end up with this equation for the wavelength that will constructively interfere. So that's what this represents. These are the wavelengths that will constructively interfere in this film. Interfere. So if you're looking at the puddle in the parking lot after rain, this is the colors that you see. So constructive interference means you are seeing those colors. Excuse me. Destructive interference, let me slide this up a little bit. We needed the waves to travel an extra half a wavelength. Since they are currently in phase, to get them out of phase, one wave needed to travel an extra wavelength farther. The extra distance, the wave that's traveling through the thin film is still traveling a distance of 2d. So down and back up. We still need this wavelength to be the wavelength in the film itself. And so we're going to get 2nd. Now, right now, we have m plus 1/2. But you're actually going to see in the test notes 2nd over m minus 1/2. And the reason why, this m value could start at 0, 1, 2, 3, so forth. And so the shortest distance would have been that m of 0. But we want to be able to use the same m values that we are using for constructive interference, meaning starting with an m value of 1. And if we do that, we have to put the minus sign in there so that the quantity of m minus 1/2, when we use the smallest m value of 1, we still get the 1/2. These represent the wavelengths that will destructively interfere, meaning we won't see them. Destructive means they cancel each other out. Their displacements cancel. Excuse me. These M values mean there are multiple wavelengths that will destructively interfere. Now, these thin films, they have to be extremely thin because not all of the light's reflected, and some of the light within the film itself will reflect back within the film. So essentially, the intensity of the light just gets smaller and smaller and smaller to a point we can't see it if the film is too thick. Now, when you do look at the table in the test notes, you'll see that there is another column that says end of the surface is less than end of the film. So the example we just solved and looked at, I wrote it up here, we were talking specifically about the surface's index of refraction being larger than the index of refraction for the film itself. And these equations, perfectly useful for that situation. But that does not need to be the only situation. It is possible to have a thin film where the surface is less, the index of refraction of the surface is less than that of the film. An example, have you ever blown bubbles? Like with kids? Or just done it because it's fun? I like blowing bubbles, can be fun, in my opinion. And so the thin film in this case is the bubble solution. And so if I was to think about the layers on this edge over here, the bubble solution is going to be this thin film. Its index of refraction is going to be greater than 1. I would assume it's probably fairly close to water. Let's say n of 1.33 just to talk about it for a second. So if we are out here, here's my terrible picture of someone looking at the bubble. The observer's over here. We are seeing light that comes in. Some of it reflects off the surface. This one, this first reflection, this wave is inverted because it is in air reflecting off of that thin film. The light that transmits through is now in the bubble solution and it reflects off. It is in a higher index of refraction, reflecting off of a lower index of refraction. This one is not inverted. So this is just the air inside of the bubble. Because one of the reflected light rays is inverted and the other is not, these two are out of phase. They're perfectly out of phase right now. And so to get them back into phase so that they interfere constructively, the extra distance traveled will need to be a multiple of half a wavelength. So when a wave is inverted, it is always inverted by, pi, not pi halves. I said pi halves before, I apologize. It's by pi because it's inverted by half a wavelength exactly. So these two waves are half a wavelength out of phase, meaning to get them back into phase, the one wave has to travel half a wavelength farther. So the distance is still 2D. We're still assuming normal incidence. We still change this to m minus 1/2 so that we can use m values that start at 1 instead of 0. And so we find that the wavelengths that will constructively interfere are described by this equation, 2nd, where n is for the film specifically, and m is this multiplier, meaning there's multiple wavelengths that will constructively interfere. But notice this equation was the destructive equation before. And again, that's because of the boundaries and the reflection. In the first situation, both light waves were inverted on reflection, which put them in phase to begin with. This one, both waves don't have an inversion, only one does. And so that puts them out of phase to begin with. That's essentially saying we have initial conditions, delta phi of pi. Similarly, the destructive equation we end up the destructive wavelengths being 2nd over m. In both situations, m is equal to 1 or 2 or 3. It's a whole number. And that just means there's multiple wavelengths that can constructively or destructively interfere. Again, constructive means what you see, and then destructive we would not see. So if we wanted to minimize reflection, we would want a destructive situation. If we wanted to maximize reflection, we would want constructive interference. As we solve our problems, we will need to identify whether n of the surface is less than n of the film, or if n of the surface is greater than n of the film. So I'm going to go through a few example problems. Once we identify that, we can then identify whether we want constructive or destructive interference and choose the appropriate equation to solve.